Hello everyone, welcome to Big Data Thoughts. Today we are going to talk about Spark execution secrets. This is basically thing that you need to know starting from how a DAG is created to how it goes to physical plan. This is extremely important to understand because then you can optimize your Spark jobs and queries very well. So let's get started. First of all, we will look at how initial Spark execution starts. What happens the moment you hit run and you submit your job? What exactly goes around in the background? So first of all, the first step is code compilation, and that happens on the client side. So you can write your code in Scala, Java, and a variety of languages. The first thing that will be done is the code compilation into a bytecode. If it is a Python, PySpark, or R, then Spark will use the driver program to interpret and translate that code. Because for Python and R, you don't need a compilation, it is an interpretation that needs to be done. So that will be done. But all in all, the first step would be to do a code compilation on the client side. Then comes the driver program. What does the driver program do? The driver program is the heart of the Spark application. And I have mentioned this in multiple videos in my Spark architecture explanation that the mastermind or the heart of the entire Spark application is the driver. It is the driver's job or it is responsible to get this execution done. So what it will do? The driver will be running on the client machine and it will be responsible for primarily three things. One, how to convert the code into a logical plan. Then managing the entire Spark session and also getting all the required resources from the cluster manager. So it's the heart and brain of the Spark cluster. It will make sure that your code is turned into a logical plan. Later on, it goes to physical, but conversion of the code into logical plan is the first step. And then also managing that entire session. Now, the next thing that would be done is a logical plan creation. So, first step is compilation, then the driver kicks in, and then comes the logical plan creation. What does it do? We all know that the basic building block in terms of creating an execution plan is a DAG, which is nothing but a directed acyclic graph. In Spark, it will create a DAG which is comprising of all the transformations that have been written in your code. This will have operations like filter, map, join, etc. Anything that you've written in your code, it will try to arrange it in a form of a DAG which is highly optimized. This there at this point of time when Spark is creating a logical plan, there is no actual computation that is getting triggered. It is just a logical DAG created out of transformations. So, and we know that Spark is a lazy execution model where it will only trigger execution when it encounters an action, not before that. So at this point, think of the logical plan as a blueprint on an architecture that you have built, but there is nothing that has actually been executed as of now. So it's just a blueprint. After this logical plan is created, then comes a very important step, which is optimization. Because Spark internally may have multiple DAGs created, but it selects the best based on which will be the most optimized one. So there are optimizers built in Spark with higher versions of Spark. They keep doing enhancements, and one of the enhancements which has been there for long is having their optimization engine, which is the Catalyst and Tungsten. So there is a Catalyst optimizer in Spark which will optimize and look at the entire logical plan because it has to do reordering of joins, simplify expressions, push filters early, which is nothing but a predicate push down. A predicate push down is doing the filters early on to reduce the amount of data. All this is being done by the Spark Catalyst Optimizer. Once the plan is converted to a physical plan, then the actual strategy of execution will come into play, and that is when Tungsten optimizer comes into play. So the catalyst one is working on the logical plan to get the best plan for you. When the execution will start, the Tungsten engine will further optimize the memory and execution on the fly. So these two are extremely important to know when we talk about optimization and performance. After we have done all of this compilation, the driver getting kicked in, the logical plan getting created, the logical plan getting optimized by the catalyst optimizer, then comes the job submission. As I said, Spark is a lazy evaluation, which means when you created the plan with transformations, nothing happened. Actual execution kicks in when you call an action like show, collect, count. At this point, what Spark will do? Spark will break the job into stages and tasks, and it will submit to one of the cluster managers. Either you will have Kubernetes, or you will have Yarn, or Mesos, or it will be a standalone one. But at this point, when the job gets submitted, then kicks in this whole process of breaking the job into stages and tasks. And I have explained this in a separate video, which I'll link in for Spark architecture. Here, this whole task of executing happens, and allocation of executors and resources will happen for the execution of the job. Then comes the part where the task execution is happening by the executors. So, what is the job of executors? The executors are the actual workhorses or workforces of the cluster. It's a distributed cluster on which Spark is operating. You have multiple worker nodes on which you can have multiple executors running depending on how many cores that that virtual machine or a physical machine, which is a worker node, has. Each task can run in parallel. It will start reading from anywhere, whether you are operating on clouds. It can be Azure cloud, it can be Amazon S3, HDFS, or local. So it will start reading. But executors are the actual workhorses or worker nodes which are running in parallel to read data and execute this whole Spark job in a distributed fashion. After that execution is done, the next step is to send back the results to the driver. So driver, as I said, is the brain and the heart of the system to give you resources, to maintain session, to collect the results back. So once the execution is done by the executors in parallel, they send the data back to the driver. And that driver's job is to now persist the data by whatever write operations have been written into the disk. This happens. So far, whatever we have looked at is all the steps that happen in the background the moment you hit run for a Spark job. Now let us look into detail in each of these things, like what is a logical plan, then what are stages, task, and physical plan. So as I said earlier, logical plan is a blueprint. Nothing has happened till now, no action, no execution, but a blueprint has been created with all the transformations as a DAG. So logical plan is the initial understanding that Spark gets from whatever you have written in your code. It understands that what you want to do with your data. It's nothing but a tree of operations, whatever operations are there in the code, like select, filter, join. And it does not think about how it will be executed. It is just creating a blueprint. Something like when we want to go somewhere, we refer a map. The map is not an execution or not an actual travel that we are doing, but it's the plan of how do we want to get there. So that's what a logical plan is, a blueprint. Now, if you see this, this is a snippet of a code just to make you understand that what will happen when I say a logical plan will get created. So a logical plan will do what? It will have steps like read from CSV, then filter rows where the amount is greater than 1000, then group by region and some amount, and then show result. That's the logical plan. It's like an algorithm or a blueprint which is saying read, filter, group by, and show. At this stage, no data is getting touched, no execution is triggered. It is just a declarative plan on how to do it. Sorry, what to do, not how to do. Why is it needed? Why do we need a logical plan? We need a logical plan because we want to do lazy evaluation. As I said, Spark will wait to execute till it gets an action like collect, write, filter. Till then, everything is a transformation and no execution is happening. So, for doing a lazy evaluation, you need a logical plan. You need a logical plan to do optimization. The catalyst optimizer has to look at a logical plan to look at what all transformations you're planning to do, and then do reordering of the operations, combining stages, maybe multiple stages into one, pushing the filters early, the predicate push down. All this is done on a logical plan. That's why logical plan is very important step in the Spark execution. Okay. So now let us look at why it is so crucial to understand the logical plan for debugging and optimization. Why are we talking so much about the steps, the logical plan? As a programmer, why do we need to know when Spark is doing that optimization in the background? It is doing it, but still it's a shared responsibility. As a developer, we need to understand the fundamentals, we need to write the code also properly. So it is important. Now, why? As I said, why would I need a logical plan for performance or for debugging? First of all, logical plan is needed to pinpoint any performance bottlenecks. How? The logical plan will tell us what transformations are being used. If there is a filter after a join, logical plan will show that there is a filter after a join. So then Spark will try to do a predicate pushdown, do a filter first and then a join, so that the data that is getting used for join is less. It will also help in reordering to get some performance gains, because if you have a logical plan, it clearly shows what are the steps. It is easier for the optimizer to now do the reordering, combine the data at some stages, like combine stages, or do a predicate pushdown. So that's one of the reasons for having a logical plan. Second, to catch any redundant inefficient operations. What does that mean? Spark may keep some unnecessary steps unless you optimize them. Okay, so by inspecting a logical plan, it is for us also that if we want to inspect a logical plan, we can do a explain, right? A dot explain function that will help you to inspect the logical plan. We can detect unnecessary shuffles, we can look at unused columns, we can detect duplicate filters. So that is the flexibility that we get to catch any inefficient operations early on. For these two reasons, it is very important to have a logical plan in place. Another thing is that, like I said, the catalyst optimizer uh, is getting run on that logical plan. So, what does this catalyst optimizer do? The catalyst engine will be used by Spark to optimize the plan. It is one thing to keep in mind is if we are writing our own user defined functions or nested queries, then it may not be perfect. So it is good to avoid any kind of complex UDF writing, because if there are inbuilt functions, Spark knows how to optimize it. If it's a UDF written by us, a complicated one, Spark may not be able to optimize it. Then logical plan will also show Spark, or basically when Spark creates a logical plan, if you do an explain and you look at it, you will know whether Spark has understood your intent correctly or not. Is it creating a correct logical plan? So that is why also it is important to have a logical plan. Another reason is to optimize joins, filters, and aggregations. We may look at the plan and see if is the join happening too soon. Is the filter getting applied properly? Are the columns getting pruned earlier? All this analysis we are able to do looking at the logical plan. Okay. So I hope this gives you a good idea of what a logical plan is and how we can use it to optimize, or how even Spark is using it to optimize our queries and code. Okay. Now let us talk a bit about DAG, because it is important. We know that DAG is the smallest, what do you call, a core component in this whole execution plan. It's the backbone of the Spark execution. If the DAG is not correct, the logical plan will not be correct, and subsequently the physical plan won't be correct. So DAG, we start with DAG, and the DAG has to be really well made by Spark, and we as a developer should know how to read that DAG. What is a DAG? DAG is nothing but a directed acyclic graph, which Spark is using to execute our code to create the plans. Now, what does these terms mean? Directed, acyclic, and graph. right? Directed means there is a task flowing in one direction. It's a directed graph. There is only flow in one direction happening. Acyclic means there are no loops, no cycles. Tasks don't revisit earlier stages. If you have completed a stage, you are done with that stage. There is no doing of the stages again. It's completely acyclic. You don't have any loop. Graph, we all know it is a network of nodes and edges, but here the nodes are operations, edges are dependencies between those operations. So Spark is creating a DAG to represent all the operations you are doing and the dependencies between them. So that's essentially a DAG. Now, how does a DAG work? After the logical plan is optimized, it will translate into a DAG of stages and tasks. Okay, so one correction, probably I probably said DAG will be created and then a logical plan. It's the other way around. Logical plan will be created and it will be translated to a DAG. DAG will have all those operations dependencies and it will tell you what are the stages and tasks. So each node is representing a transformation and the edges are nothing but dependency and the execution order, because we said that it is a directed graph in one direction. So that gives you the execution order. If you look at this piece of code where it's the same one that we saw earlier, what will DAG do? DAG is nothing but a translation of that logical plan. Logical plan had these 4-5 steps. So DAG will represent this 5 steps of reading a CSV, a filter, a group by, an aggregate, and then showing the results. So show is the action here where the actual execution starts. Rest are all transformation. Filter is an action, show is an action. Okay. Now, why is this important? Why is a DAG important? It is important for us to look at the parallelism. So DAG will allow Spark to split the work into independent tasks. It will tell what should be the stage, what should be the task. So Spark knows that these are the tasks that have to be run in parallel. It also represents resilience. If a task fails, then how will Spark do the recomputation? It will not start from the beginning, it will start from the point of failure. So that lineage or that resilience is given by the DAG. There is no need for Spark to now go and rerun the whole job. This DAG gives you resilience or information to Spark in terms of where it failed and from where to start back. It is an optimized execution. So DAG is dividing into stages and minimizing all the data shuffles and maximizing speed. Now, shuffles are a big problem in a distributed system with huge data. Shuffle means you are taking data from one node to other. We want to minimize that. So DAG will create a plan of stages in such a way that this shuffle is optimized and reduced. Okay. Now, since we spoke about stages and tasks, from when the DAG creates stages and tasks, we have to understand what is a stage, what is a task, and how is your complex code or operation getting broken down into stages and tasks. So, what are stages? A stage you can think of as a group of operation that can be executed together. It's like a transaction in a SQL world where you have a set of operations getting executed together without getting the data to be shuffled. We want to minimize shuffle, so stages are created in such a way that it is always a group of operations which will not require data shuffles. Spark will divide a DAG into multiple stages based on the shuffle boundaries. How does Spark decide what should constitute one stage? Which operations in your code should be grouped together as a stage? Simple principle, any operations that can be grouped together without doing any shuffles. That's a stage for Spark. So that's how it divides your program and operations into multiple stages. Each stage, think of it as a set of tasks. So the hierarchy is a job, then a stage, then a task. So a stage is a collection of tasks that can run in parallel. And task is your smallest unit. Then comes the task. What is task doing? Task is the smallest unit of execution. Job will have multiple stages, stage can have multiple tasks. Each task is a piece of the stage that runs on a single partition of data. So what is stage? Stage is what runs without doing shuffles, a group of operations. Task is something which is a piece of the stage because the stage can have multiple tasks, and this runs on a single partition of data. If you have 200 partitions, Spark will try to create 200 tasks so that you are operating on a particular partition of data in that task. All this is done to make sure that we are not taking data here and there in the cluster. If you take a real world example, stage is the recipe and task is our individual chefs who are doing their part in the meal. So to prepare a meal, you may have 10 steps, cutting some vegetables, preparing some marination. So you give it to different chefs to do it parallelly and bring together the recipe. So think of stage as the recipe or a plan, and task is those individual chefs working to get that meal together. Let us look at how a stage is broken up. So we understood what is a stage, what is a task, but how does it look like? If you look at this piece of code, we are reading two Parquet files, and then we are trying to do a join and a group by and an aggregation before we write it out. So in Spark, if it has to break into stages, what it will do? It will try to make sure that the read, the filter, and the map are one stage. The shuffle is the second stage. Group by and aggregation is again the third stage, and fourth stage is write to disk. You see narrow and wide here. What does it mean? There are narrow transformations, there are wide transformations. Narrow transformations are which do not require shuffling of data because you're reading, filtering, and mapping the data on that data partition. But when you talk about join, you have to shuffle data across the network. That's a wide transformation. It involves shuffling. If then after joining, you can again do group by and aggregation on the smaller partitions on the executor. So that's a narrow transformation. And then you write to the disk. So this is to give you an overview of how will stages be created out of the plan. Now let's look at the last step in our execution. We looked at logical plan, we looked at task, stage, all in detail. Now let's look at the final step, which is the physical execution, where the rubber actually meets the road. This is what? This is creation of a physical plan. So there was a logical plan built, which was optimized by a catalyst optimizer. Now comes the time to generate a physical plan. This is where all your abstract transformations are going to get translated into a sequence of executable steps because your executors will need executable steps to do the actual execution. So now the blueprint is getting turned into a construction manual. I'm giving these examples so that you can relate to it better. The logical plan was the blueprint of the architecture. Now you're creating a detailed construction manual for the implementation. What are the steps here? The steps here are to have a DAG. From that DAG, you create a physical plan. So you have a logical plan, then you create a DAG, you optimize, and then you create a physical plan. The physical plan will have the operators, the execution strategy, and so let's start one by one, right? DAG, what it will do, it will show you a very high level flow of what needs to be done and in what order. It gives you the execution order. Physical plan will be the exact set of instructions on how to do it. Till the DAG, we were trying to just do a plan for what to do. Physical plan is how to do. It is a specific set of instructions and which algorithms that you will use to do the execution. This plan will have your operators and execution strategy, which means it will decide whether you should do a sort merge join or a broadcast join. That strategy. In logical plan, you just said a join. But what kind of join is now getting decided? The stage boundaries are getting decided, which means determining where the shuffle will happen in the DAG. Then the task assignment, breaking the stages into multiple tasks and mapping it to specific executors. That is getting done. The precise execution order is getting done. After all this is done, there will be multiple physical plans that will get created. Okay, and then Spark will do a comparison, a cost based analysis, a comparison to get the best physical plan out of the ones that Spark created. After we get the best physical plan, the concrete instructions are sent to the executors to execute and produce the result. That is getting done by Spark. So now we understood till physical plan. Now, so this part is clear, but we need to understand the bottlenecks. What are the two major things which can cause our plans not to work efficiently? Even if Spark does a very good logical plan, physical plan, there can be issues. So we as a developer need to ensure some things on our side to make sure the plan is really an optimized one. So two things we need to know: shuffles and skews. First of all, shuffle. What is shuffle? As the name suggests, we are trying to shuffle the data across the network. Whenever you have a wide transformation, like when you are joining data, you have to do, or a group by, you have to do a shuffle of data across the network. It is extremely expensive, and the biggest time that is taken in any distributed setup is for shuffling. So, if Spark needs to reorganize data across partitions, there will be a shuffle. For example, in terms of group by, joins, reduce by, wherever data with the same key needs to come together, there will be a shuffle. What are the key triggers to shuffle? When does shuffle get triggered? Like I said, where there are wide transformations like group by, join, distinct, repartition, sorting, for all of this, you have to do a lot of shuffling. So we need to avoid these kind of operations in our code, and we need to partition our data really well. The second bottleneck is data skews. What is a skew? In simple terms, skew is when one partition has significantly more data than the other. It's we say it's skewed. One partition has thousands of rows, other partition has very few. So it defeats the purpose of partitioning the data. That's why we have to have a partition with low cardinality. We have to select partitions in such a way that they are well distributed. Data is well distributed. It can happen, data skew can always happen if you select a wrong partition key. This will mean that certain tasks will take much longer than the overall other task. So if there are multiple tasks running in parallel, if you have a heavy partition running on that, the task running on that will take more time. The others will finish off quicker, but the job cannot finish. These are stragglers, right? These tasks which are dragging all the entire job. Then there has to be a thought put into selecting the right partition key so that data is not skewed, right? And why are these getting bottlenecks, the skews and the shuffles? Because they will slow down the job. The shuffles will slow down the job due to heavy network traffic and disk writes of shuffling the data. Like I said, the skews will cause straggler tasks which will just drag and drag because of the huge amount of data in the partition. The other tasks will finish, but we will still be held up because of the straggler task. So together, skews and shuffles are the biggest reasons for our queries to be inefficient or taking longer time. So we as developers definitely have to focus on these two, right? And I just want to give one more analogy for this skew and shuffle. Think of shuffle as rearranging all the books in a library based on an author. If you have to arrange all the books in the library based on the author, you have to literally look at every book and take them to different places. So that's shuffling. You are taking everything here and there and then arranging. Data skew is if you have one author who has thousands of books and other authors have one book, two book, 10 books. So when you arrange one author, books by author, you will get one particular partition which is one author with huge amount of books and the others very very small. So that's the analogy for a shuffle and a skew in terms of the real world. I hope today's video will really help you to understand what is happening in the background and what is Spark up to when we hit a submit on the job button. So keep liking and sharing to the videos, and please subscribe to the channel to get more interesting videos. Thank you. Thank you everyone.